Okay, so this is a problem out of Taylor's Mechanics, solution 1.16. What I would say is just please like and subscribe real quick because it helps me out. I'm going to be posting a lot of videos working different problems from Taylor's to Griffith's quantum mechanics and electrodynamics. So if you wouldn't mind liking and subscribing, I would appreciate it. And if you'd like to suggest a problem, you can on Twitter at PhysicsHelping. All right, so let's get into the problem. So we have a scalar product, r dot s, and we have equation 1.7, which says that the dot product, r dot s, is the summation of ri times si. So that the Pythagorean theorem implies that the magnitude of any vector r is r equals the square root of r dot r. Okay. So for part A, we start with this. We know any two vectors dotted with each other is just the summation. You just multiply like this. We've done this for a while. This is equation 1.7, pretty straightforward. Just the definition of the dot product. So now, let's dot r with itself. So again, nothing crazy here. Just now we're going to have r and then another r here. And this is just going to be x times x plus y times y plus z times z. If we just defined r as being x hat plus y hat plus z hat. And this is, of course, x squared plus y squared plus z squared, which is, of course, just r squared. So what we have then is the dot product of r with itself is just r squared, and then squaring both sides we can see r is the square root of r dot r. That's all we needed to show. That was part A. Okay, for part B, it's clear that the length of the vector does not depend on our choice of coordinate axes. The results of part A guarantee that the scalar product r dot r, as defined by 1.7, is the same for any choice of orthogonal axes. Use this to prove that r dot s, as defined by 1.7, is the same for any choice. Consider the length of the vector r plus s. Okay, so we're going to look at the vector r plus s, so some different vector. And we're going to actually look, if we take the magnitude and square that, well, we can rewrite this as r plus s dotted with r plus s, right? This is the exact same thing. This is essentially what we have. We did this basically in part A. So we can take this vector r plus s and rewrite it like this. So basically the end of part A, just imagine if we squared, instead of the vector r, we had the vector r plus s. Okay, cool. So let's go ahead and expand this. What do we get? Well, we get r dot r plus 2 r dot s, so just essentially distributing here, plus s dot s. So we just distributed on the right hand side. Okay, so now this is equal to what we said it was. And we're going to solve for the dot product of these two, since that's what we're interested in. And we also know r dot r is r squared, and s dot s is s squared, again from part A. So we get 2 r dot s equals what we had on the right hand side, and then we subtract off an r squared and an s squared. And what we see here is that there's really no direction. All these are lengths. This is a length, this is a length, this is a length, this is a length. Obviously the 2 is just a scalar. So there's no direction involved here, so the choice of our coordinate axes are not relevant. So that was problem 1.6, part A and B. If that helped you at all, please leave a like and subscribe, and I will post more